What if the universe didn't begin with a bang, but with a whisper so delicate, so perfectly synchronized, that it set the stage for everything we see today? Picture this, the first moments of existence, not as chaos, but as a dance of particles moving in flawless harmony. This is the mystery of quantum coherence, the hidden rhythm that might hold the key to understanding how our universe came to be. Think of it like the first note in a symphony, so precise that it dictated the entire melody of reality. And today, we're diving deep into this cosmic enigma, exploring 30 groundbreaking theories about how quantum coherence shaped the earliest moments of everything. For centuries, we've wondered how the universe sprang into being. Was it random? Was it destined? Or was there something far more elegant at work, a kind of quantum choreography that brought order to the chaos? Quantum coherence is the idea that particles can act in unison, like a flock of birds turning as one, even across vast distances. In the first fractions of a second after the Big Bang, this phenomenon could have been the invisible hand that sculpted the cosmos, ensuring galaxies, stars, and planets formed just right. Without it, the universe might have been a tangled mess, a place where life could never take hold. That's how powerful this concept is. It's not just a footnote in physics, it's the potential foundation of everything. And here's the most thrilling part. We're on the brink of uncovering its secrets, from cutting-edge experiments that recreate the conditions of the early universe to mind-bending theories that stretch our understanding of reality. Scientists are piecing together the puzzle of quantum coherence like never before. Some believe it could even hint at a deeper layer of existence, a hidden structure beneath space and time itself. So if you've ever looked up at the night sky and wondered how it all began, you're about to embark on a journey that will challenge everything you thought you knew. This isn't just a story about the past, it's a glimpse into the very fabric of reality, and by the end, you'll see the universe in a whole new light. The first theory takes us back to the very edge of time itself, before atoms, before light, even before space as we know it. Imagine a void, not empty but teeming with energy, a seething quantum foam where particles flicker in and out of existence in a heartbeat. These are quantum fluctuations, tiny ripples in the fabric of reality itself. And according to this idea, it wasn't a violent explosion that birthed the universe. It was one of these fluctuations, magnified and stabilized by quantum coherence. Think of it like a single note resonating through a silent room, growing louder and more defined until it becomes a symphony. In those first moments, coherence could have acted like an invisible conductor, ensuring these fluctuations didn't just collapse back into nothingness, but instead expanded into the universe we see today. What's astonishing is that we might have evidence for this written across the sky. The cosmic microwave background, that faint glow of radiation left over from the universe's infancy, shows patterns, tiny variations in temperature that look almost like fingerprints. Scientists believe these patterns could be the echoes of those primordial quantum fluctuations, stretched across billions of light years by the universe's expansion. If that's true, then the universe didn't just erupt randomly. It was shaped by an underlying order, a coherence that turned chaos into structure. But here's where it gets even more fascinating. Some researchers argue that without quantum coherence, those early fluctuations would have cancelled each other out, leaving behind a featureless void. Instead, coherence might have acted like a cosmic glue, aligning these fluctuations just enough to allow matter to clump together, forming the seeds of galaxies. It's like tossing a handful of pebbles into a pond. If the ripples overlap just right, they create a stable pattern. But if they're out of sync, the surface just churns with noise. The universe, it seems, got the timing perfect. And this isn't just speculation. Modern physics is starting to catch up with these ideas. Experiments with ultra-cold atoms and quantum systems are showing how coherence can emerge spontaneously, even in the most chaotic conditions. If the same principles applied in those first moments, it would mean that the birth of the universe wasn't a fluke, but the inevitable result of quantum laws playing out on a cosmic scale. So when we look at those subtle patterns in the cosmic microwave background, we might actually be glimpsing the universe's first coordinated act, a whisper of order in what should have been pure chaos. Now let's shift our gaze to something even more mind-bending. What if the universe's first moments weren't unfolding in 3 dimensions at all, but on a flat, 2-dimensional surface like a cosmic projector screen? This is the holographic principle, a radical idea that suggests everything we perceive, space, time, matter, might just be a shimmering illusion, a kind of shadow cast by quantum coherence playing out on a distant, invisible boundary. Think of it like a fingerprint. The swirling ridges you see aren't the story itself, but a compressed code of something far richer. In those first instants, coherence could have been etched into the universe's edges like a blueprint, with our 3D reality unfolding from it like a hologram. This idea didn't come out of nowhere. It's rooted in the strange behavior of black holes. When matter falls into one, it doesn't just vanish. According to quantum mechanics, information can't be destroyed, so physicists believe it gets smeared across the black hole's event horizon, the point of no return. That surface becomes a frenzied ledger recording every detail of what fell in. Now, stretch this concept to the entire universe. If a black hole's contents can be encoded on its 2D boundary, why couldn't the whole cosmos work the same way? The holographic principle takes this leap, proposing that the early universe's coherence wasn't a 3D phenomenon, but a flat, perfectly synchronized dance written on the fabric of spacetime itself. What's wild is that this might not just be philosophy. Science could test it. In labs around the world, researchers are creating analog black holes using ultra-cold atoms or even sheets of plasma, studying how information scrambles across their surfaces. If they find patterns matching holographic predictions, it could mean our universe really does operate like a cosmic hard drive, with coherence as its underlying operating system. Even more tantalizing, some string theorists argue that the holographic principle isn't just a quirk of physics, it's a necessity. The math suggests that higher dimensions might collapse into lower ones through coherence, like a symphony being transcribed into sheet music. Every note, every instrument perfectly preserved just in a form we're only beginning to decipher. So where does that leave us? If the holographic principle holds, then quantum coherence wasn't just a feature of the early universe, it was the canvas. Every galaxy, every atom might just be a projection of something far simpler, far more elegant. And as experiments inch closer to testing these ideas, we might finally uncover whether reality is as deep as it seems, or if we're all just reading the universe's first coherent whisper, written in 2 dimensions, echoing across eternity. But what if the fabric of spacetime itself was woven from something far stranger, tiny, interlocking loops of quantum energy? That's the bold claim of loop quantum gravity, a theory that reimagines the universe not as smooth and continuous, but as a vast, dynamic network of spinning threads. Picture a cosmic tapestry, each thread vibrating with its own rhythm, yet perfectly synchronized with the others, a dance so precise it creates the illusion of seamless space and time. In this view, the earliest moments of the universe weren't ruled by random chaos, but by a deep, underlying coherence, a structure so fine-grained it operates at the Planck scale, where a single unit of space is a trillion times smaller than an atom. At the heart of this idea are spin networks, intricate webs of quantum connections that encode the geometry of spacetime itself. Think of them like the pixels on a screen, but instead of static dots, each one is a tiny loop of energy, spinning and interacting with its neighbors. In those first moments after the Big Bang, these loops could have aligned in perfect harmony, their collective spin creating a stable framework for the universe to emerge. It's as if the cosmos booted up from a quantum operating system, with coherence acting as the code that prevented glitches, no crashing, no errors, just the flawless execution of reality. And here's where it gets even wilder. Recent simulations suggest this might not just be theoretical. Scientists using supercomputers have modeled how these spin networks could spontaneously form coherent structures, even under the extreme conditions of the early universe. The results are striking, like watching a chaotic storm of quantum threads suddenly snap into a symmetrical lattice, as if guided by an unseen hand. Some researchers argue this could explain why the universe didn't immediately tear itself apart in those first fiery instants. Coherence in this scenario wasn't just a happy accident, it was the scaffolding that held everything together, but the implications go even deeper. If spin networks are real, they might solve one of physics' greatest puzzles: how to bridge quantum mechanics and gravity. Einstein's theory describes spacetime as smooth and bendable, while quantum mechanics deals in jagged, discrete jumps. Loop quantum gravity suggests both are true. Spacetime is smooth on large scales, but up close it's a shimmering mesh of quantum links. And coherence could be the ghost in the machine, the hidden force that merges these two worlds seamlessly. Imagine a river that looks calm from a distance, but under a microscope you see it's made of countless droplets, each one moving independently, yet collectively flowing as one. That's the universe according to this theory, a quantum river with coherence as its current. So when we peer into the depths of space or study the tiniest particles, we might actually be glimpsing the echoes of this primordial spin network. Every galaxy, every star, even the empty space between them could be traced back to those first coherent loops, a cosmic legacy written in spins and threads waiting to be decoded. While the holographic principle and loop quantum gravity paint the early universe as a symphony of synchronized threads or a two-dimensional code, another idea takes us even deeper, into the very fabric of emptiness itself. Imagine a void so full of potential that it crackles with energy even at absolute zero, the coldest temperature possible. This isn't science fiction, it's zero-point energy, the restless hum of quantum fields that never truly settle. And according to this fourth theory, it might have been the spark that ignited the universe's first coherent dance. Traditional inflation theory tells us the cosmos expanded exponentially in its first sliver of a second, driven by a mysterious field that briefly dominated everything. But the zero-point energy hypothesis flips the script. Instead of a sudden, unexplained push, it suggests the universe's expansion was seeded by quantum fluctuations in this relentless background, energy fluctuations that, thanks to coherence, didn't just fizzle out but amplified into something monumental. Picture a calm lake where tiny ripples, instead of fading, suddenly sync up and surge into a wave. That's what coherence could have done for those primordial quantum jitters, given them direction, structure, and the power to shape spacetime itself. What's fascinating is how this contrasts with classic inflation. Inflation assumes a sudden, uniform stretching of space, smoothing the universe into the homogeneous expanse we see today. But zero-point energy offers a subtler origin story, one where coherence acts like a cosmic conductor, ensuring those initial fluctuations didn't just explode randomly but harmonized into the patterns we now detect in the cosmic microwave background. In other words, inflation might have been the universe's crescendo, but zero-point energy was the tuning fork that set the pitch, and the evidence isn't purely theoretical. Lab experiments with Casimir plates, tiny metal surfaces placed nanometers apart, reveal the eerie grip of zero-point energy. When brought close enough, they're subtly pushed together by the sheer pressure of quantum fluctuations in the empty space between them. If such effects can warp matter on microscopic scales, why couldn't they, amplified by coherence, have warped the entire infant universe? Some physicists even speculate that zero-point energy didn't just seed expansion. It might still be fueling it today, hidden in what we call dark energy. But here's the twist. If zero-point energy was the universe's first choreographer, it challenges the idea of a clean Big Bang. Instead of a singular explosion, we might be looking at a quantum ripple that grew legs, a fluctuation so perfectly coherent that it cascaded into reality. That wouldn't just reshape our origin story. It'd mean the universe didn't emerge from nothingness, but from a sea of infinite potential, waiting for the right rhythm to take hold. And if that's true, then every atom in existence might still carry the echo of that first, perfectly synchronized quantum whisper. What if our universe wasn't the first or the only attempt at reality? Imagine a sea of countless possible worlds flickering in and out of existence, each a slightly different variation of physics, dimensions, or even time itself. Among this infinite chaos, one universe hours stumbled upon the perfect balance of quantum coherence, a fleeting moment where particles align just right to create stability. This is the multiverse quantum decoherence theory, a mind-bending idea suggesting our cosmos didn't emerge from nothingness, but from a cosmic filtering process where only the most coherent universe survived. At the heart of this theory lies a paradox. Quantum mechanics tells us particles exist in superpositions, multiple states at once, until observation collapses them into a single outcome. Now stretch that idea to the scale of universes. In the multiverse landscape, countless versions of reality could have existed simultaneously, each a quantum possibility vying for stability. But most would have succumbed to chaos, their particles too disorganized to sustain structure. Our universe, however, might have been the exception, a rare instance where decoherence, the process that collapses quantum superpositions, favored harmony over disorder. Think of it like a million radios playing static, with one suddenly tuning into a crystal-clear signal. That signal is us, the universe that clicked into coherence. Sean Carroll and other physicists exploring this idea argue that decoherence isn't just a quirk of quantum experiment. It could be the universe's natural selection. In the multiverse, universes with unstable quantum states would rapidly unravel, while those with coherent structures endure. It's survival of the fittest, but for reality itself. This could explain why our universe seems so finely tuned for complexity, from the precise strength of gravity to the exact mass of electrons. If every fundamental constant was a roll of the dice, coherence might have been the winning hand, the one arrangement where particles didn't just interact, they cooperated. But how do we test something as abstract as a collapsing multiverse? Surprisingly, clues might lie in the quantum noise around us. Experiments with superconducting qubits, tiny circuits that mimic quantum behavior, show how decoherence can select stable states from a sea of possibilities. When scaled up, this same process could have played out cosmically, with our universe emerging as the most viable configuration. Even more tantalizing, some models suggest that the cosmic microwave background's faint anomalies, those tiny temperature variations, might carry imprints of other universes bumping against ours before decoherence sealed our fate. The implications are staggering. If this theory holds, the Big Bang wasn't a beginning but a continuation, a moment when infinite possibilities narrowed into one coherent thread. And that thread, our universe, might still be entangled with others, like echoes of roads not taken. It's a humbling thought. Every star, every atom might exist because somewhere in the quantum fog, a multitude of worlds faded away, leaving only the one that could sing in perfect harmony. Roger Penrose's vision of the cosmos isn't just about beginnings, it's about rebirth. His conformal cyclic cosmology theory paints a universe that doesn't end with heat, death, or collapse, but resets like a phoenix rising from its own ashes. Imagine a cosmic cycle where each iteration, called an eon, begins with a burst of quantum coherence, a perfect alignment that sets the stage for a new universe to unfold. But here's the twist: the remnants of past eons might still linger, etched into the faint glow of the cosmic microwave background like ghostly fingerprints. At the heart of Penrose's idea is a radical rethinking of scale. As the universe expands toward infinity, all matter eventually evaporates into radiation and distances become meaningless. In this stretched-out, featureless state, the end of one eon seamlessly blends into the beginning of the next, with quantum coherence acting as the bridge between them. Think of it like a movie reel where the final frame of one film dissolves into the opening shot of the next. No hard edges, just continuity. The laws of physics reset, but the echoes of what came before might remain, imprinted in the fabric of space-time itself. And those echoes could be hiding in plain sight. Penrose and his collaborators claim to have found concentric rings in the CMB subtle patterns of temperature variation that defy conventional explanations. These rings, they argue, might be collision scars from supermassive black holes in a previous eon, their gravitational waves rippling through the birth of our own universe. It's as if the cosmos has a memory, a way of preserving the most cataclysmic events across cycles of destruction and revival. Skeptics point out that these patterns could be statistical flukes, but if verified, they'd be the first tangible evidence that our universe isn't the first and won't be the last. What makes this theory so compelling is how it reframes entropy, the usual villain of cosmic endings. Instead of a universe winding down into disorder, Penrose suggests coherence could periodically reboot the system, turning infinite disorder into a blank slate. It's a bit like shaking a snow globe just when everything seems settled. A flick of the wrist sends the flakes swirling anew. In this view, quantum coherence isn't just a one-time event at the Big Bang. It's the rhythmic pulse of existence itself, a cosmic heartbeat that keeps time across eons. The implications are as profound as they are poetic. If Penrose is right, the universe isn't a single story but an endless saga, with each chapter written in the language of quantum synchronization. And those faint rings in the CMB, they might be the universe's way of whispering to us from beyond the veil of time, hints that coherence isn't just a feature of reality, but its eternal choreographer. The universe might have chosen its own structure through a process eerily similar to natural selection, but instead of biological traits, it was quantum states being put to the test. This is quantum Darwinism, the idea that certain coherent configurations survived the chaos of the early cosmos not by chance, but because they were the most resilient, the most fit to transition from quantum weirdness to the stable reality we know. Picture a cosmic sieve where trillions of potential quantum states flickered into existence, but only those that could consistently interact with their surroundings without collapsing into noise endured long enough to shape the universe. At its core, quantum Darwinism suggests that what we perceive as classical reality, the solid, predictable world of planets and particles, isn't the default state of things. It's the exception, the handful of quantum configurations that were robust enough to be repeatedly observed and reinforced by their environment. Think of it like a forest after a wildfire. Countless seeds may scatter, but only the ones with traits suited to the scorched earth will take root. In the early universe, coherence acted as that selective pressure, amplifying states that could communicate their existence across multiple scales while filtering out fragile, fleeting possibilities. This process of quantum selection might explain one of physics' deepest puzzles: why the universe transitioned from a probabilistic quantum fog to the definite, measurable reality we see today. Experiments in quantum decoherence show how particles lose their superposition when interacting with their surroundings, like a spinning coin finally settling on heads or tails. But quantum Darwinism goes further, proposing that certain states weren't just randomly collapsed. They were chosen because they could redundantly imprint themselves on the environment. A photon's polarization, for example, might stabilize into a measurable state not by accident, but because that particular alignment could be read by countless other particles around it, creating consensus. The implications for cosmology are profound. If quantum Darwinism governed the early universe, then galaxies, cosmic voids, and even the laws of physics themselves could be the result of a billion-year selection process. Fluctuations in the primordial quantum field that were too delicate or isolated would have faded into oblivion, while those that could entangle with larger swaths of space-time, forming coherent, self-reinforcing patterns, became the scaffolding for stars and planets. It's as if the universe conducted its own symphony, discarding discordant notes until only the most harmonious melodies remained. Critically, this isn't just philosophical speculation. Labs studying quantum systems from diamond defects to superconducting qubits have observed how preferred states emerge through environmental interaction, mirroring the proposed cosmic selection. Even the cosmic microwave background's eerie uniformity might be a fossil of this process, a snapshot of the quantum states that achieved enough consensus to imprint on the universe at large. But here's the most humbling twist. If quantum Darwinism is correct, our entire reality could be a kind of collective hallucination, a set of quantum states so persistently observed that they've become the universe's baseline. Other configurations might still exist flitting at the edges of perception, but they're the cosmic equivalent of endangered species, outcompeted by the robust, redundant states we call home. So when we measure a particle's spin or map the distribution of galaxies, we're not just exploring the universe, we're witnessing the survivors of an ancient quantum competition where coherence was the ultimate judge. Take a gas and cool it to nearly absolute zero, and something bizarre happens. Particles lose their individuality, merging into a single quantum entity that moves as one. This is a Bose-Einstein condensate, a state of matter where coherence reigns supreme. Now imagine that same phenomenon, but on a cosmic scale. The entire infant universe, not as a fiery chaos, but as a vast, ultra-cold condensate, its particles locked in perfect harmony. This theory suggests that in those first moments, the cosmos wasn't just hot and dense. It was a quantum superfluid, a sea of synchronized energy where coherence didn't merely exist, it dictated the rules. What makes this idea so compelling is how neatly it solves one of cosmology's biggest puzzles, inflation. The universe expanded faster than light in its first fraction of a second, a process that defies classical physics. But if space itself was a Bose-Einstein condensate, its superfluid properties could explain that explosive growth without invoking unknown forces. Picture honey pouring from a jar, normally slow and viscous, but if all its molecules suddenly moved in unison, it'd flow effortlessly. That's the power of coherence, turning resistance into synchrony, allowing the universe to stretch without tearing. And the echoes of this primordial condensate might still linger. Some physicists argue that dark energy, the mysterious force accelerating cosmic expansion, could be a remnant of that early superfluid state. Just as a cooled condensate exhibits zero viscosity, dark energy seems to permeate space without friction, pushing galaxies apart as if the vacuum itself has memory of its coherent past. Even stranger, certain quantum vacuum theories propose that space isn't truly empty but filled with a dynamic, superfluid-like medium. Experiments with ultra-cold atoms in labs have shown how such superfluids can mimic cosmic expansion, creating miniature Big Bangs where coherence drives rapid growth. But here's where it gets truly mind-bending. If the universe began as a condensate, then its structure, galaxies, black holes, even time, might be quantum turbulence frozen into form. When a superfluid rotates, it doesn't swirl smoothly. It fractures into tiny whirlpools called vortices. Scale that up, and those vortices could have seeded galaxy clusters, their spin preserved across billions of years. It's as if the cosmos remembers its superfluid origins, its largest structures tracing back to microscopic quantum dances. Critics argue that the extreme cold required for a condensate clashes with the searing heat of the Big Bang. Yet proponents counter that temperature is relative. What matters isn't absolute heat but coherence. In the dizzying energy of the early universe, particles might have achieved a different kind of cold, a quantum harmony that transcended thermal noise. After all, coherence isn't about lack of energy, it's about alignment. A symphony isn't silent, but its power comes from every instrument playing in time. Whether or not this theory holds, it reshapes how we view cosmic origins. The universe's first act may not have been a blast of destruction, but a whisper of synchronization, a fleeting moment when everything, everywhere moved as one. And if remnants of that coherence still linger in the fabric of space, then dark energy isn't just a mystery, it's a relic of the universe's most perfect harmony. Imagine a universe where every force, gravity, electromagnetism, even the nuclear interactions, were once indistinguishable, blended into a single, symmetrical superforce. Then, in an instant, that perfect symmetry shattered like glass, and from the fragments emerged the distinct forces that shape our reality today. This is the symmetry-breaking scenario, a pivotal moment when quantum coherence didn't just organize matter, it birthed the very rules that govern it. At its core, symmetry breaking is a bit like cooling water into ice. When water is liquid, it looks the same no matter how you turn it. It has perfect rotational symmetry. But as it freezes, that symmetry breaks. Ice crystals form in specific orientations, locking the water into a rigid, less symmetrical structure. In the early universe, something eerily similar happened with quantum fields. At unimaginably high energies, these fields were perfectly symmetrical, their forces interchangeable. But as the cosmos expanded and cooled, that symmetry fractured, and coherence dictated how the pieces fell. The Higgs mechanism offers the clearest parallel. Before particles gained mass, the Higgs field permeated the universe like an invisible syrup, uniform and symmetrical. But when the temperature dropped below a critical threshold, the field condensed into a new state, like water settling into ice, breaking the symmetry and giving particles mass as they interacted with it. This wasn't random, it was a quantum phase transition guided by coherence. The Higgs didn't just assign mass haphazardly, it did so in a way that preserved stability, ensuring electrons, quarks, and other particles emerged with precisely the properties needed to build atoms, molecules, and eventually us. But the Higgs is just one example. Symmetry breaking likely orchestrated the separation of all four fundamental forces. In the universe's first trillionth of a second, the electromagnetic and weak nuclear forces were unified as a single electroweak force. Then coherence-driven symmetry breaking split them apart, like a cell dividing into specialized descendants. Gravity and the strong nuclear force may have undergone similar splits even earlier, at energies so extreme we can only glimpse them in particle colliders or the aftermath of cosmic inflation. What's striking is how delicate this process was. For symmetry breaking to produce a universe like ours, the phase transitions had to be exquisitely timed. Too abrupt, and the cosmos would have been riddled with defects, cosmic strings, or magnetic monopoles that disrupted structure. Too slow, and the universe might have lacked the heterogeneity needed for galaxies to form. Coherence acted as the universe's tempo keeper, ensuring the transitions were smooth, synchronized, and critically irreversible. Today, we see echoes of this everywhere. The fact that neutrinos have mass, that protons outnumber antiprotons, even the very existence of matter over antimatter, all these trace back to symmetry breaking events where coherence tipped the scales. It's as if the universe had 1,000 possible paths, but coherence funneled it down the one where life could emerge. And that's the real marvel. Symmetry breaking didn't just create forces, it curated the conditions for complexity, turning a featureless quantum soup into a cosmos rich with possibility. At the smallest scales of existence, what if space-time isn't smooth and continuous, but more like a shifting puzzle? Its pieces constantly rearranging until the universe cools enough to lock them into place. This is quantum gravity, a radical theory proposing that the coherence of spacetime didn't emerge from nothing, but from a cosmic phase transition akin to water crystallizing into ice. In the earliest moments, the fabric of reality might have been a buzzing network of disconnected nodes, a formless quantum foam where every point in space was equally connected to every other. But as temperatures plummeted, those frenzied connections froze into a stable lattice, creating the structured spacetime we recognize today, a cosmic metamorphosis where chaos gave way to order through coherence. Picture a pot of molten metal cooling into a solid. At high heat, atoms move freely, sliding past one another with no fixed arrangement. But as the metal hardens, those atoms settle into a rigid grid, their positions now defined by crystalline symmetry. Quantum gravity suggests spacetime underwent a similar transformation. In the searing heat of the Big Bang, the universe's underlying quantum links were fluid and ever-changing, a soup of potential geometries. Then, as expansion diluted the energy, those links chose a configuration, snapping into a stable pattern like cosmic frost forming on a window pane. This transition didn't just create space and time, it imbued them with coherence, ensuring that distant particles could interact predictably, that cause and effect would hold across the cosmos. What's astonishing is how neatly this solves one of quantum gravity's biggest headaches: how to reconcile the smooth spacetime of general relativity with the granular, quantized world of particles. In the quantum gravity model, spacetime is granular at its core, but its coherence emerges from the collective behavior of countless microscopic links, much like the rigidity of a diamond arises from the precise alignment of carbon atoms. Even more intriguing, the theory predicts that if you could probe spacetime at unimaginably tiny scales, trillions of times smaller than an atom, you'd find remnants of that primordial disorder, like defects in a crystal where the lattice didn't quite align. These defects could manifest as exotic particles or even dark matter, cosmic relics of the moment when the universe chose its structure. But here's where it gets truly visionary. If spacetime froze into coherence like a crystal, then its properties, the speed of light, the strength of gravity, might not be fundamental constants, but accidents of that freezing process. Tweak the initial conditions, and you'd get a universe with entirely different physics. Some researchers even speculate that quantum gravity could explain why our universe has 3 spatial dimensions. Just as ice crystals form in specific geometries dictated by atomic bonds, spacetime's lattice might have naturally stabilized into the dimensions we experience, with others remaining frozen out as unstable or incoherent. The echoes of this great cosmic freeze might still be detectable. Just as crystals vibrate at specific frequencies, spacetime's lattice could resonate with quantum noise, subtle ripples that future gravitational wave detectors might catch. And if they do, it would mean that the fabric of reality isn't just something we move through, it's a dynamic quantum structure that remembered how to align itself, a testament to the universe's first and most profound act of synchronization. What if our universe wasn't born from a singularity, but from something far stranger, the belly of a black hole? This is the black hole genesis theory, a daring idea that reshapes not just our cosmic origin story, but the very nature of reality itself. Picture a black hole in some other universe, its crushing gravity warping spacetime into oblivion. But instead of ending in destruction, that collapse triggers a quantum rebirth, a tunneling event where coherence bridges the gap between annihilation and creation. In this scenario, the overwhelming density inside a black hole doesn't lead to an infinite dead end, but to a new beginning, a universe like ours bursting into existence like a cosmic phoenix. At the heart of this idea is physicist Nikodem Poplawski's work, which applies a fascinating twist to Einstein's equations. Normally, black holes are seen as one-way doors, their event horizons marking the point of no return. But Poplawski suggests that at the very center, the extreme torsion, a twisting of spacetime itself, could reach a limit, rebounding like a spring compressed too far. This bounce wouldn't just be a random explosion, it would be a coherent quantum process, a tunneling event where the black hole's interior flips into a new state. A nascent universe with its own laws, its own spacetime, all born from the ashes of its parent. Think of it like a seed pod bursting open, but instead of scattering seeds, it releases an entire cosmos. The implications are staggering. First, it solves one of the biggest puzzles about black holes: what happens at the singularity. Instead of infinite density-breaking physics, the torsion-driven bounce preserves quantum coherence, turning a mathematical nightmare into a creative act. Second, it hints that our universe might not be the first or only one. Every black hole in existence could be a potential universe generator, each with its own unique physics. We might even be living inside one right now, the distant descendant of some primordial black hole from a higher dimensional reality. And here's where it gets even wilder. If this theory holds, the cosmic microwave background, the afterglow of the Big Bang, might carry faint imprints of that parent black hole's structure. Some researchers speculate that certain anomalies in the CMB, like unexpected temperature fluctuations or large-scale asymmetries, could be echoes of that earlier universe's final moments. It's as if the cosmos remembers its birth, a quantum memory etched into the sky. But how would coherence play into this? In the chaos of a collapsing black hole, quantum tunneling isn't guaranteed. It requires precise alignment to avoid total annihilation. Coherence acts as the universe's lifeline, ensuring the tunneling event isn't just random, but structured enough to produce a stable new reality. Without it, the rebound could fizzle into chaos, leaving nothing but scattered particles. Instead, coherence orchestrates the transition, shaping the newborn universe's initial conditions with just the right balance of order and freedom. Critics argue that testing this idea seems impossible. After all, we can't peek inside a black hole. Yet subtle clues might exist. If our universe emerged from a black hole, its early expansion would carry unique signatures, like a preferred direction or residual torsion effects hidden in gravitational waves. Future telescopes probing the universe's earliest moments could hunt for these fingerprints, turning speculation into science. Ultimately, this theory blurs the line between destruction and creation. Black holes, long seen as the universe's ultimate endpoints, might instead be cosmic wombs, places where quantum coherence weaves catastrophe into genesis. And if that's true, then every star, every galaxy, even the empty space between them, could trace back to a singular moment when a dying reality whispered its last coherent breath and birthed our own. But what if quantum coherence wasn't just a happy accident of the universe, but a necessity, a cosmic prerequisite for life itself? This is the anthropic coherence principle, a provocative twist on the anthropic principle that suggests the universe's early synchronization wasn't random, but inevitable, because only a coherent cosmos could ever produce beings capable of questioning it. It's like a cosmic version of the observer effect. We're here to measure the universe's coherence precisely because coherence made our existence possible. And that raises a haunting question: did the universe conspire to create us? Or are we just witnessing the one version of reality where all the quantum dice rolled perfectly? The anthropic principle has long been a lightning rod in cosmology. At its core, it's the idea that the universe's fundamental constants, the strength of gravity, the mass of electrons, even the density of dark energy, appear eerily fine-tuned for life. Tweak any one of them slightly and stars wouldn't form, atoms would fly apart, or the cosmos would collapse in on itself. Critics dismiss this as a tautology. Of course, we observe a life-friendly universe. We couldn't exist in one that wasn't. But the anthropic coherence principle takes this further, arguing that it's not just constants that had to align, it was the very process of quantum synchronization. Without coherence stitching the early universe together, those finely tuned constants wouldn't matter because structure itself would have unraveled before stars could ignite. Imagine building a house of cards in a hurricane. Even if you had the perfect cards, the slightest instability would send them scattering. Coherence, in this analogy, isn't just the cards, it's the steady hand that stacks them against the wind. In the primordial universe, that steadiness might have come from quantum entanglement on a cosmic scale, with particles linking up in ways that reinforced stability rather than chaos. Some physicists, like Leonard Susskind, suggest this could explain why we don't see universes with almost coherent laws. They're not just uninhabitable, they're inherently unstable, collapsing before they can even form atoms. But here's where the multiverse pushes back. If infinite universes exist with random physical laws, then of course we'd find ourselves in the rare one where coherence and constants align. It's the ultimate lottery, trillions of cosmic tickets with only a handful capable of hosting life. The anthropic coherence principle counters that even in a multiverse, coherence isn't just another variable, it's the scaffolding that makes any universe possible. Without it, most hypothetical universes wouldn't just be lifeless, they'd be formless, dissolving into quantum noise before they could even inflate. It's the difference between a library with every possible book and a library where most pages are blank, or worse, where the ink never dries. The debate rages because both sides flirt with metaphysics. Is coherence a fundamental law woven into the fabric of reality, or is it a fluke, a fleeting alignment in an ocean of cosmic chaos? Some theorists, like Lee Smolin, propose a middle path. Universes might learn coherence over time, with black holes birthing new universes that inherit slightly more stable physics from their predecessors. In this view, our universe isn't the first attempt, it's the latest iteration in an evolutionary chain, refined by trial and error until coherence became inevitable. What's undeniable is how deeply coherence is tied to life's potential. From the quantum bonds that stabilize DNA to the precise resonance of atomic orbitals that make chemistry possible, coherence isn't just a cosmic luxury, it's the silent architect of complexity. And if that's true, then the anthropic principle isn't just about why we're here, it's about why here had to exist at all. The universe didn't just stumble into coherence. It needed to. David Bohm's pilot wave theory was long dismissed as a fringe idea until now. This radical reinterpretation of quantum mechanics suggests particles aren't just probabilistic waves collapsing randomly, but guided by a hidden force, an invisible hand steering their path. Apply this to the early universe, and suddenly the Big Bang wasn't a chaotic explosion. It was a choreographed dance with quantum coherence acting as the conductor. Imagine a cosmic ocean where every particle is a tiny boat, not tossed by chance waves, but riding the crest of a deeper, more fundamental current, a pilot wave sculpting spacetime itself into galaxies, stars, and planets. Recent experiments with bouncing droplets have breathed new life into this once controversial idea. When tiny silicone drops are placed on a vibrating fluid bath, they don't move randomly, they're guided by waves they themselves create, eerily mirroring quantum behavior. Scale this up to the universe's first moments, and you get a breathtaking possibility. The infant cosmos might have behaved like that fluid, its particles guided by a universal pilot wave that dictated structure from the outset. Instead of randomness birthing stars, coherence could have drawn the blueprint, ensuring matter clustered in just the right way to form cosmic webs and voids. Critics once argued pilot wave theory was needlessly complex, adding hidden variables where randomness sufficed. But the early universe presents a unique problem. Randomness alone can't easily explain its staggering uniformity. The cosmic microwave background's near-perfect symmetry, the even distribution of galaxies across billions of light-years, these aren't hallmarks of chaos. They're fingerprints of something far more deliberate. Bohm's guiding wave offers an elegant solution, coherence as the universe's first architect, ensuring fluctuations didn't just scatter wildly, but followed an embedded order like ripples tracing the contours of a pond. And the implications don't stop there. If the pilot wave model holds, quantum entanglement, spooky action at a distance, isn't so spooky after all. Entangled particles might simply be riding the same underlying wave, their fates intertwined from the beginning. This could explain why the universe's large-scale structure looks eerily connected. with galaxies aligning in vast filaments as if pulled by invisible threads. It's not magic, it's coherence operating at scales we're only beginning to comprehend. The most tantalizing clue lies in quantum turbulence. Just as fluid experiments show droplets creating intricate wave patterns, simulations of the early universe reveal vortices in quantum field structures that, if guided by a pilot wave, could have seeded galaxy clusters. Some theorists even suggest dark matter could be a relic of this primordial guidance system, an invisible remnant of the waves that once shaped reality. Bohm's vision was decades ahead of its time, but now, as we peer deeper into quantum fluids and cosmic maps, his idea of a guided universe feels less like philosophy and more like a roadmap, a hidden script written in the language of coherence waiting to be decoded. And if he was right, then every atom, every star might not be the product of chance, but of a harmony older than time itself. What if gravity isn't a fundamental force at all, but a side effect of something deeper, something hidden in the universe's very first coherent whispers? Eric Verland's entropic gravity theory flips our understanding of the cosmos on its head, suggesting that what we call gravity might just be the universe's way of keeping track of quantum information. Think of it like a cosmic librarian, not organizing books but arranging the fabric of reality itself, ensuring every particle, every wave fits into a grander pattern. And at the heart of this idea lies coherence, not just as a feature of the early universe, but as the glue that bound entropy and structure into a single, elegant dance. When we talk about entropy, we usually think of chaos, a room getting messier over time, energy dispersing into useless heat. But Verland's vision is different. In his framework, entropy isn't just disorder, it's stored information, a record of how things are arranged. And in the early universe, when coherence ruled, that information wasn't scattered. It was perfectly organized, like a symphony where every note is accounted for. Gravity, according to this theory, emerges from the universe's need to maximize entropy, but not in a destructive way. Instead, coherence acted as a guide, ensuring that entropy didn't dissolve structure but sculpted it, like a master artist chiseling order from seeming chaos. The implications are staggering. If gravity is truly entropic, then the universe's first moments weren't governed by warps in spacetime alone. They were shaped by an invisible quantum ledger, a cosmic spreadsheet keeping track of every particle's position and energy. Coherence, in this view, was the system that kept the ledger balanced, preventing errors that might have torn reality apart. Picture a vast, interconnected network where every fluctuation, every quantum blip is logged and adjusted in real time. Without that coherence, the ledger would have devolved into noise, and gravity, as we know it, might never have formed. And here's where it gets even more fascinating. Verland's math suggests that dark matter, that elusive substance holding galaxies together, might not be a particle at all. Instead, it could be a shadow of this entropic accounting, an artifact of the universe's need to reconcile its quantum books. Just as a hologram encodes 3D information on a 2D surface, dark matter might encode the gravitational memory of coherence, a relic of how the early universe balanced its equations. Some simulations even show that entropic gravity models can reproduce galactic rotation curves without invoking invisible matter, as if the universe's first coherent structures left behind a ghostly fingerprint. But how do we test something so abstract? Clues might lie in the voids between galaxies, where gravity behaves in ways Newton and Einstein can't fully explain. If entropic gravity is real, these cosmic deserts should show subtle deviations from classical predictions, deviations that coherence could have seeded in the universe's infancy. Future telescopes mapping the large-scale structure of the cosmos might spot these anomalies, turning speculation into hard science. What's beautiful about this idea is how it unifies the universe's extremes. The quantum and the cosmic, the chaotic and the ordered, all bound together by coherence acting as the universe's first accountant. It's a reminder that even in the seeming randomness of entropy, there's a deeper logic, a rhythm that began with the universe's first coherent breath and still echoes in the pull of every star, the orbit of every planet. So the next time you feel gravity's tug, remember, you might not just be falling toward Earth. You're following a path laid down by the universe's oldest, most meticulous bookkeeper. The Boltzmann brain paradox is one of the most unsettling ideas in cosmology. What if the universe we perceive isn't real, but just a fleeting thought in the mind of a disembodied brain that randomly assembled from quantum fluctuations? Statistically, in an infinite universe, disordered chaos should dominate over order, making the accidental formation of a single self-aware brain infinitely more likely than the emergence of entire galaxies, stars, and civilizations. Yet here we are, seemingly surrounded by structure, not chaos. This is where quantum coherence steps in, not as a cosmic fluke, but as the hidden rulebook that stacked the deck in favor of ordered reality. Think of it like a deck of cards, shuffle them endlessly, and you'd expect randomness, but if the cards were subtly magnetized, certain arrangements would appear far more often than chance alone could explain. Coherence in the early universe might have acted like that invisible magnetism, guiding quantum fluctuations toward stable, complex structures instead of transient chaos. The Boltzmann brain scenario assumes randomness is king, but coherence suggests the game was rigged from the start, not by design, but by the universe's own quantum grammar favoring synchronization over disorder. Recent work in quantum thermodynamics reveals something astonishing. Coherent systems resist entropy longer than disordered ones. A laser beam, for example, maintains its focused light far beyond what randomness would predict because its photons march in lockstep. Apply this to cosmology, and the early universe's coherence could have been a thermodynamic lifeline, extending the window for structure to form while suppressing freak Boltzmann fluctuations. It's not that isolated brains couldn't emerge, it's that coherent processes made galaxies, stars, and planets so overwhelmingly probable that Boltzmann anomalies became cosmic afterthoughts. Critics argue that even with coherence, infinite time and space should still spawn countless Boltzmann brains. But there's a catch: coherence isn't just about probability, it's about persistence. A random brain might flicker into existence, but without a coherent framework to sustain it, it would dissolve as quickly as it formed. Stable minds require stable universes, and stability is coherence's specialty. The cosmic microwave backgrounds whisper thin temperature variations, the delicate balance of gravitational constants. These aren't accidents. They're relics of a universe that chose coherence over chaos, making Boltzmann brains not just statistically unlikely, but structurally unsustainable. Here's the twist: if coherence really did tilt the cosmic scales, then reality as we know it might be more than just an unlikely victory against entropy. It could be the universe's most natural state, a testament to how deeply synchronized the fabric of existence truly is. And that changes everything, because suddenly, the question isn't why we exist, but why anything else ever could. Imagine the universe as a hologram where all the information needed to describe every star, galaxy, and quantum particle isn't stored in the three-dimensional space we see, but on a two-dimensional surface at its edge. This bizarre idea isn't science fiction. It's the essence of the AD/CFT correspondence, a revolutionary concept in theoretical physics that suggests our entire cosmos might be a projection from a lower dimensional reality. At its core, this duality proposes an astonishing trade-off: the chaotic quantum dance of particles in a boundary theory, like a flat, distant screen, could perfectly encode the orderly, coherent structure of an entire universe unfolding within it. To grasp how this could work, think of a video game. What you see on your screen, the sprawling landscapes, intricate characters, isn't stored pixel by pixel. Instead, it's generated in real time by simpler underlying code. The AD/CFT correspondence suggests something similar for reality. the coherent behavior of gravity and space-time in our universe, the bulk, might emerge from a completely different, seemingly unrelated set of rules governing particles on a faraway boundary, the CFT, or conformal field theory. The mind-bending part, those boundary particles don't look like they're describing a universe, they're just interacting in a flat, gravityless space. Yet through the lens of this duality, their interactions are the universe translated into a higher dimensional form. What makes this so groundbreaking for quantum coherence is the way it solves one of physics' biggest headaches: how to reconcile gravity with quantum mechanics. In the bulk universe, gravity behaves smoothly, warping space-time like a stretched sheet. But on the boundary, there's no gravity at all, just particles obeying quantum rules. The AD-S/CFT correspondence bridges these worlds by suggesting that the orderly, coherent structure of space-time is encoded in the entangled quantum states of those boundary particles. It's as if the universe's coherence isn't a local phenomenon but a holographic mirage emerging from a hidden quantum ledger. This idea isn't just theoretical sleight of hand. Experiments with quantum computers are starting to simulate simple holographic systems, where the behavior of entangled qubits mirrors the dynamics of a higher dimensional space. In one notable study, researchers found that increasing entanglement on the boundary directly affected the geometry of the simulated bulk, as if stitching together quantum threads on a flat surface somehow stitched space-time itself into existence. If this holds, then the coherence we see in the cosmos, the way galaxies cluster, the uniformity of the cosmic microwave background, might trace back to quantum entanglement on a shadow boundary we can't even see. But here's where it gets even stranger. The AD-S/CFT correspondence implies that the universe's quantum order isn't just a product of local interactions but a global, almost mathematical inevitability. In the same way, a symphony isn't just the sum of its notes but the relationships between them. Coherence might be less about individual particles and more about the information shared between them across dimensions. Some theorists argue this could explain why the early universe was so astonishingly uniform. Its coherence wasn't built piece by piece but downloaded whole from a boundary where quantum rules allowed no other outcome. Critics point out that our universe isn't perfectly described by AD-S/CFT. The AD-S stands for anti-de Sitter space, a simplified model with negative curvature, while our cosmos is closer to flat or positively curved. Yet, even with this mismatch, the duality offers a profound insight. Coherence might not be something the universe achieves, but something it inherits, woven into reality from a deeper, more fundamental layer. Whether this holographic principle applies exactly to our universe or not, it reshapes how we think about order, structure, and the very nature of existence, suggesting that the quantum whispers of a distant boundary might still be echoing through the stars. What if the universe didn't just move through time but was built from it? This is the startling premise of the time crystal hypothesis, a theory that reimagines the cosmos not as a static stage where events unfold, but as a dynamic, repeating structure where time itself pulses with the precision of a quantum metronome. Nobel laureate Frank Wilczek first proposed this radical idea in 2012, suggesting that just as ordinary crystals have atoms arranged in repeating spatial patterns, time crystals exhibit structure in the fourth dimension, their components oscillating in perfect, self-sustaining cycles without any energy input. Now imagine scaling this up to the universe's infancy. If space and time were forged in that primordial furnace, could coherence have locked the entire cosmos into a vast, cosmic-scale time crystal, its rhythm echoing through every particle and galaxy that followed? The implications are as beautiful as they are bizarre. Time crystals aren't just theoretical curiosities, they've been created in labs, from diamond lattices with entangled nitrogen vacancies to chains of ytterbium atoms chilled near absolute zero. These experiments reveal something extraordinary. When systems reach a state of extreme quantum synchrony, they can break time symmetry, meaning their ground state, their lowest energy configuration, isn't static but ticks like a clock. Apply this to the early universe, and suddenly the Big Bang's aftermath looks less like an explosion and more like the first chime of a cosmic grandfather clock, with coherence ensuring every subsequent tick built structure rather than chaos. Here's where it gets even wilder. Wilczek's math suggests that in the presence of certain quantum fields like those thought to permeate the early universe, time crystals could form spontaneously, their oscillations driven by the fabric of reality itself. Picture a hall of mirrors where every reflection isn't just an image, but a moment in time, perfectly preserved and repeating. In this view, the universe's expansion might not have been a one-way street, but a rhythmic pulse with coherence acting as the drummer keeping the beat. Some cosmologists speculate this could explain the universe's startling regularity, the even distribution of galaxies, the uniformity of the cosmic microwave background. These aren't accidents, they're the universe's first coherent rhythm, frozen into the cosmos like grooves in a vinyl record. But the most tantalizing clue comes from black holes. Recent work by physicists like Norman Yau shows that time crystals near a black hole's event horizon could exhibit time dilation echoes, subtle repetitions in their oscillations due to extreme gravity. If the early universe behaved similarly, remnants of those echoes might still linger in gravitational wave data, like faint drumbeats from the dawn of time. Future observatories like the Einstein telescope could hunt for these signals, turning speculation into evidence. Critics argue that time crystals today are tiny, fragile things, far removed from a universe-spanning structure. Yet scale might not be the barrier we assume. Just as ice crystals grow from a single seed, a primordial time crystal could have nucleated from a microscopic quantum fluctuation, its coherence spreading like a wave until the entire cosmos pulsed in sync. And if that's true, then every second we experience, every tick of the clock, might not be time passing but time remembering, replaying the universe's first perfect rhythm, set in motion 13.8 billion years ago by the quietest, most profound metronome of all, quantum coherence. Quantum mechanics has always had an uneasy relationship with reality. Do particles exist in definite states, or only as probabilities until we look? The quantum Bayesian approach, or cubism, takes this dilemma and flips it entirely. What if quantum states aren't descriptions of the world at all, but personal beliefs, tools an observer uses to navigate uncertainty? Apply this to the universe's birth, and suddenly, coherence isn't an objective feature of the cosmos. It's the shared language that emerged when countless quantum observers agreed on what reality should be. At its core, cubism treats quantum mechanics less like a rulebook for particles and more like a user manual for prediction. When a scientist says an electron is in a superposition, they're not claiming it's physically smeared across space, they're expressing their own uncertainty. They're betting odds for where it'll appear when measured. Now rewind to the universe's first moments. If reality was a seething quantum foam, cubism suggests coherence didn't happen passively. It was negotiated, a consensus reached among countless nascent observers, each collapsing their own version of events until a stable, shared universe crystallized. Think of it like a group hallucination, but one where the hallucination builds the world. This idea isn't just philosophy, it's backed by the strange math of quantum decision theory. When two observers update their beliefs based on shared data, their predictions can synchronize, creating what looks like objective reality. Scale this up to the cosmic level, and the universe's coherence might be the ultimate example of this synchronization, a quantum democracy where every interaction casts a vote for structure over chaos. Critics argue this veers into solipsism, but cubists counter that shared experience is reality, the only one that matters. After all, isn't science itself a form of consensus? The stakes are dizzying. If cubism is right, then the universe's coherence isn't written into the fabric of space-time. It's a story we're all telling together, a narrative so consistent we mistake it for the absolute truth. And that raises a haunting question. If observers are the architects of reality, what does that mean for the cosmos before life arose? Some cubists propose retroactive coherence, that the universe's early moments gained structure in anticipation of future observers, like a tree falling in a forest only if someone eventually hears it. Others suggest prebiotic processes could have played the observer role with chemical reactions, measuring quantum states into stability. The controversy cuts to the heart of science itself. Is the universe an independent truth waiting to be discovered, or a collaborative project shaped by the act of looking? Cubism doesn't dismiss objectivity, it redefines it as the overlap of countless subjective worlds. And if that's true, then quantum coherence isn't just the universe's first miracle. It's the moment we all started agreeing on what miracle even means. Einstein's most famous equation connected energy to matter, but what if his later work secretly tied quantum entanglement to the very fabric of space itself? That's the bold claim of the ER=EPR conjecture, a theory so radical it suggests wormholes and quantum coherence might be two sides of the same cosmic coin. Picture two particles entangled across the universe, their fates linked no matter the distance. Now imagine that connection isn't just mathematical, it's physical, a microscopic tunnel stitching space together from the inside out. This is the heart of ER=EPR. The idea that every quantum handshake might have forged a hidden bridge in spacetime itself, weaving coherence into the universe's foundation. The theory's name is a mashup of two landmark physics concepts. Stands for Einstein-Rosen bridges, those hypothetical wormholes dreamed up in 1935 as shortcuts through spacetime. EPR refers to the Einstein-Podolsky-Rosen paradox, the same year's bombshell paper highlighting entanglement's eerie non-locality. For decades, these ideas lived in separate worlds, until physicists Leonard Susskind and Juan Maldacena proposed they were secretly one and the same. In their vision, when particles become entangled, an invisible wormhole forms between them, not as a sci-fi passageway, but as a geometric manifestation of their quantum bond. It's as if the universe keeps its books balanced not with abstract equations, but with real, physical threads, tiny bridges ensuring coherence spans the cosmos. Here's where it reshapes our cosmic origin story. If entanglement builds spacetime, then the early universe's staggering coherence wasn't just a happy accident, it was infrastructure. Picture the Big Bang's aftermath as a quantum construction site, where every new particle pair wasn't just linking up but laying down invisible scaffolding for reality itself. The more entangled particles formed, the more spacetime fabric they wove, until the universe's structure emerged not top-down from gravity, but bottom-up from quantum connections. Some models even suggest black holes are this process turned up to 11, their interiors crisscrossed with bridges like cosmic knotwork, their event horizons encoding entanglement on a scale we're only beginning to fathom. Lab experiments are now putting this idea to the test. In quantum simulators, researchers have created holographic analogs of wormholes using entangled qubits, watching as manipulating one particle instantly affects its partner, not through magic but through an emergent geometry that mirrors an bridge. Other teams are probing the entanglement entropy of black holes, hunting for signatures that their event horizons might literally be woven from quantum threads. If these hints hold, they'd confirm that coherence isn't just a feature of reality, it's the loom on which reality was built. But the wildest implication. ER=EPR might solve physics' biggest headache, uniting quantum mechanics with gravity. If spacetime is a network of entanglement, then gravity isn't a fundamental force, it's the collective tension of countless quantum links pulling the cosmos into shape. Coherence, in this view, was the universe's first architect quietly spinning entanglement into existence, and existence into entanglement, So the next time you hear about particles communicating instantly across light years, remember, they might not be breaking the rules of space. They might be revealing its true, threadbare nature. What if the universe isn't just governed by equations, but by something far more primal, rules as simple as the ticking of a clock or the flipping of a light switch? This is the wild premise of the cellular automaton universe, a theory that reimagines reality as a vast quantum-powered grid where every particle, every force, is just a cell following basic computational instructions. Stephen Wolfram, the visionary behind this idea, suggests that beneath the apparent chaos of the cosmos lies a hidden order, not from complex laws, but from tiny, discrete steps playing out like cosmic clockwork. And at the heart of it all, coherence, emerging not as a miracle, but as the inevitable outcome of trillions of simple interactions clicking into place. Picture a chessboard stretching to infinity, where every square isn't just a static space but a tiny computer. Each cell updates its state based on the states of its neighbors, following rules as straightforward as if 3 neighbors are active, become active. From these minimalist beginnings, patterns emerge: gliders, pulsars, even structures that resemble living organisms. Now scale this up to the universe. Instead of pixels on a screen, imagine spacetime itself as a grid, with every Planck-sized volume processing quantum information according to basic algorithms. Coherence, in this view, isn't some exotic phenomenon. It's what happens when enough cells synchronize, their collective behavior giving rise to the stable, predictable reality we recognize. What's astonishing is how closely this mirrors quantum behavior. In Wolfram's models, even simple rules can produce entanglement like correlations between distant cells, as if the universe is running a cosmic version of Conway's game of life. Particles aren't independent entities but patterns propagating through the grid, their interactions dictated by the underlying code. This could explain why quantum mechanics feels so counterintuitive. It's not that particles are mysterious, but that we're seeing the shadows of a deeper computational layer. But the real magic happens when these cellular automata exhibit classical behavior. Despite their discrete rules, large-scale patterns often smooth out into continuous-looking phenomena, just as pixels blend into an image when viewed from afar. This might be the secret behind the universe's coherence. At our scale, the computational grit vanishes, leaving only the illusion of seamless spacetime and unbroken causality. It's like watching a flipbook. Individual frames are jerky, but flip them fast enough and motion looks fluid. Critics argue that reducing reality to computation strips away its beauty, but Wolfram's work suggests the opposite. The richest complexities, galaxies, consciousness, even mathematics itself, could emerge from rules no more complicated than those governing a Sudoku puzzle. And if that's true, then the universe's first moments weren't about equations running on some abstract cosmic computer. They were about coherence crystallizing from the humblest beginnings, one cellular click at a time. The implications are staggering. If the universe is a cellular automaton, then quantum weirdness, superposition, collapse, even the observer effect, might just be artifacts of the grid's architecture. Dark matter may be just inactive cells, dark energy, a glitch in the rules propagating outward. And if we ever crack the universe's source code, we might not just understand reality, we could, in principle, rewrite it. For now, the theory remains speculative, but it's a thrilling reminder. Coherence might not be the universe's starting point, but its greatest emergent masterpiece, a symphony composed by a trillion tiny metronomes, each ticking to the same simple beat. Imagine every event in the universe, every particle collision, every cosmic dawn, even the Big Bang itself, as a negotiation between past and future, where reality is forged through a quantum handshake across time. This is the heart of the transactional interpretation, physicist John Cramer's radical reimagining of quantum mechanics. In this view, coherence isn't just about particles aligning in space, it's about the universe conducting a dialogue with itself, where the present emerges from countless offers sent backward and confirmations echoed forward through time. Rewind to the cosmos's first moments, and you'd witness a symphony of these handshakes, each one sculpting the newborn universe into something stable, structured, and astonishingly coherent. At its core, the transactional interpretation flips causality on its head. Normally, we think of waves of probability flowing forward in time, but Kramer's math suggests they also flow backward, like ripples meeting in a pond. When a particle is emitted, it sends an offer wave into the future. When absorbed, it returns a confirmation wave to the past. The overlap of these waves, what Kramer calls the transaction, is what we perceive as reality. Now zoom out to the Big Bang. Instead of a singular explosion, picture a quantum storm of offer and confirmation waves resonating across the newborn cosmos, their interference patterns locking into place like cosmic Velcro. Coherence in this scenario wasn't a top-down law but a bottom-up consensus, forged through countless transactions that agreed on the universe's structure. What's mesmerizing is how neatly this explains quantum weirdness. Take the double-slit experiment where particles seem to know whether they're being observed. In Kramer's framework, this isn't spooky action, it's just future detectors sending confirmation waves backward, shaping how the particle behaves. Apply this to cosmology and the universe's eerie uniformity. The fact that opposite edges of the cosmos look identical despite never being in contact stops being a paradox. Those regions were in contact not through space but through time, their coherence negotiated via transactions before the first stars flickered to life. Critics argue the transactional interpretation introduces unnecessary metaphysical baggage. Why invoke backward in-time waves when conventional quantum mechanics works fine? But recent experiments with quantum retrodiction predicting past states from future measurements are teasing out hints that the past might indeed be malleable. In one study, physicists manipulated entangled particles in ways that only made sense if future choices were subtly influencing earlier events. It's as if the universe keeps its books balanced not just across space, but across time, with coherence acting as the ledger. The most radical implication: if transactions define reality, then the Big Bang might not have been a beginning at all, just the moment when the universe's quantum checks and balances reached equilibrium. Every atom, every galaxy could be the residue of a handshake between what was and what would be, a cosmic pact written in the language of coherence. So when you look up at the night sky, you're not just seeing light from distant stars. You're witnessing the aftermath of the universe's oldest conversation, a dialogue that began before time and continues in every quantum heartbeat of existence. Picture a laser, not the everyday kind, but something far grander, a cosmic-scale resonator where the very fabric of space-time acts like the mirrored cavity that amplifies light. Now swap the light for gravity, and you've got the quantum gravity cavity theory, a mind-bending idea that reimagines the early universe as a kind of quantum echo chamber, where coherence wasn't just a happy accident but an inevitable consequence of the cosmos's own geometry. In this view, the Big Bang wasn't an explosion in empty space, it was the first pulse of a gravitational laser, with the universe's boundaries acting like perfect mirrors, reflecting and reinforcing quantum fluctuations until they locked into a stable, synchronized rhythm. The elegance of this idea lies in its borrowed physics. Lasers work because photons bouncing between mirrors stimulate the emission of identical photons, creating a coherent beam. Apply that logic to gravity, and you get a universe where space-time itself, through its boundary conditions, could have amplified quantum coherence on a cosmic scale. Think of it like a drumhead vibrating at just the right frequency, where the edges constrain the vibrations to form standing waves. In the quantum gravity cavity, those edges might have been the universe's own topology, a closed geometry, or even a higher dimensional structure that trapped gravitational waves, forcing them to resonate in harmony rather than scatter into noise. What's striking is how this solves one of cosmology's thorniest problems: how quantum coherence could persist long enough to shape the universe without collapsing under its own turbulence. In a cavity, coherence isn't fragile, it's self-reinforcing, like a choir singing in a cathedral where the acoustics amplify every note. The universe's expansion would have eventually opened this cavity, releasing the coherent gravitational waves we now see imprinted as subtle ripples in the cosmic microwave background. Those ripples aren't just relics of the past, they're the universe's first resonant hum, a gravitational lullaby that set the stage for everything to come. But here's the twist: this theory doesn't just explain coherence, it might also predict it. If the early universe was a quantum gravity cavity, then the coherence we observe wasn't a fluke but a mathematical inevitability, as unavoidable as the pitch of a tuning fork. Some models even suggest that dark matter could be a remnant of this resonant phase, a shadow of those standing gravitational waves that never fully dissipated. And if that's true, then the cosmos isn't just expanding, it's still humming, its coherence now stretched thin but echoing in the voids between galaxies. The beauty of this idea is how testable it could be. Just as laser cavities leave telltale spectral lines, a quantum gravity cavity would have imprinted specific frequencies on the universe's gravitational wave background. Future observatories like LISA or the Einstein telescope might detect these faint reverberations, turning a wild hypothesis into hard science. Until then, the theory stands as a reminder. Sometimes the universe's deepest order doesn't come from chaos but from resonance, a perfect note struck at the dawn of time, still vibrating through every atom in existence. Some of the universe's deepest secrets might be hidden in knots, not the tangled strings of everyday life, but exquisitely twisted quantum states that could have woven the fabric of reality itself. This is the promise of topological quantum field theory, a framework where particles don't just move through space but stitch it, their interactions leaving indelible marks on the cosmos like threads in a grand tapestry. Picture the earliest moments after the Big Bang not as a chaotic fireball, but as a quantum loom where particles called enyons, exotic entities that remember their paths like cosmic breadcrumbs braided around one another in precise patterns. These weren't random dances, they were the universe's first act of topological order, a delicate choreography that might have imprinted coherence onto spacetime itself. The magic of enyons lies in their bizarre statistics. Unlike fermions and bosons, which forget their past encounters, enyons carry a memory of every twist and turn they've taken relative to one another. When two enyons swap places in a two-dimensional plane, their quantum wave functions don't just revert to normal, they gain a phase shift, a kind of geometric scar encoding their journey. Now imagine billions of these particles in the early universe, braiding and fusing in intricate cycles. Each twist would have subtly altered the quantum fields around them, like invisible fingers kneading dough, until the entire cosmos bore the imprint of their coherence. This isn't just abstract math. Lab experiments with fractional quantum Hall systems have shown enyons behaving exactly this way, their braiding producing stable, error-resistant quantum states, precisely the kind of robustness needed to sculpt a universe from formless energy. But here's where it transcends mere particle physics. In topological quantum field theory, spacetime itself could emerge from these braids. Think of it like weaving a sweater. The yarn isn't the sweater, the pattern of knots and loops is. Similarly, the universe's four dimensions might not be fundamental, but the consequence of countless quantum threads braiding into a stable, coherent structure. Some models even suggest that gravity, Einstein's curvature of spacetime, could be a side effect of this topological order, with enyon braids generating what we perceive as warps and ripples in the cosmic fabric. It's as if the universe booted up not from equations, but from a silent symphony of knots tightening and loosening in perfect rhythm. the echoes of this process might still reverberate today. Just as imperfections in a crystal reveal its growth history, certain anomalies in the cosmic microwave background, regions where temperatures fluctuate unexpectedly, could be scars from primordial onion braiding. Even dark matter might fit into this picture. Some theorists propose it's not a particle at all, but a topological defect, a knot in spacetime's weave that never fully unraveled. Future quantum computers designed to simulate onion dynamics could test these ideas by recreating mini-universes in silicon, watching as coherence emerges from virtual braids. What's breathtaking is how this flips our view of cosmic origins. The universe's order wasn't imposed from above, it crystallized from below, from the bottom-up interplay of quantum threads twisting into stability. And if that's true, then every galaxy, every star, might owe its existence to a silent ballet of onions dancing in the dark before time began. Imagine a ghostly sea of particles so elusive that trillions pass through your body every second without a trace. Neutrinos, the universe's most aloof wanderers. Now picture them in the earliest moments of the cosmos, not as solitary phantoms, but as a synchronized collective, a neutrino condensate so dense and coherent it could have steered the destiny of everything we see today. This isn't science fiction, it's a daring hypothesis that these nearly massless particles, often dismissed as cosmic afterthoughts, might have been the unseen architects of dark matter and the large-scale structure of the universe. At first glance, neutrinos seem like terrible candidates for cosmic choreography. They barely interact with matter, flitting through planets and stars like shadows through a sieve. But rewind to the universe's first second, and conditions were anything but ordinary. Temperatures soared above 10 billion degrees, compressing neutrinos into a superheated soup so dense that even these evasive particles couldn't ignore one another. In this primordial pressure cooker, something extraordinary may have happened. Neutrinos could have formed a Bose-Einstein condensate, a quantum state where individual identities blur and particles march in lockstep. Think of it like a crowd of strangers suddenly moving as a single organism, their chaotic motions replaced by perfect harmony. This neutrino condensate wouldn't have been just a curiosity. It could have solved two of cosmology's greatest puzzles at once. First, dark matter. If a fraction of those primordial neutrinos slowed and clumped as the universe cooled, their combined gravity might explain why galaxies rotate faster than visible matter alone can account for. Unlike ordinary neutrinos, which zip through space at near-light speeds, condensate neutrinos could have been sticky, their coherence acting like quantum Velcro, tugging them into the cosmic scaffolds that later birthed galaxies. Second, the universe's vast web of filaments and voids. Simulations show that dark matter distributed in a coherent, wave-like pattern, exactly what a neutrino condensate would produce, matches the observed structure of the cosmos eerily well. It's as if the blueprint for reality was drawn in the invisible ink of synchronized neutrinos. The smoking gun might lie in the cosmic microwave background. Tiny fluctuations in this afterglow reveal how matter was distributed in the universe's infancy. Some theorists argue that certain anomalies, subtle dips and peaks in the CMB's power spectrum, could be fingerprints of neutrino condensates imprinting their coherence onto spacetime. Even more tantalizing, recent experiments like Katrin are tightening limits on neutrino mass, and if these particles turn out to be just heavy enough to cluster gravitationally, the condensate hypothesis gains serious traction. Critics counter that neutrinos are too energetic to form stable condensates on cosmic scales, but proponents point to a loophole. What if an unknown force, a hidden interaction between neutrinos, locked them into coherence long enough to shape the universe before they dissolved into the background? It's a long shot, but nature has surprised us before. After all, neutrinos were once thought to be massless until experiments proved otherwise. Whether or not this theory holds, it reframes our cosmic origins. If neutrinos, the universe's most ephemeral particles, could orchestrate its grandest structures, then coherence isn't just about brute force, it's about leverage, about finding harmony in the most unexpected places. And that changes everything. Because if something as fleeting as a neutrino can leave a mark on eternity, what other invisible dancers might still be shaping the cosmos quietly in the dark? Chaos and order might seem like opposites, but what if the universe's coherence emerged precisely from the tension between them? This theory flips the script on cosmic origins, suggesting that the early universe didn't start with perfect synchronization. Instead, it began in a roiling quantum chaos, a storm of fluctuations so wild and unpredictable that order seemed impossible. Yet hidden in that turbulence was a secret, the seeds of coherence waiting for the right moment to crystallize. Think of it like a thunderstorm giving way to a rainbow, not by chance, but because the laws of physics demand it. Nonlinear dynamics, the study of how complex systems evolve, offers a startling clue. In everything from fluid turbulence to predator-prey cycles, systems often teeter on the edge of chaos before suddenly self-organizing into patterns. The same could have been true for the infant cosmos. Imagine quantum fields vibrating at random, their fluctuations canceling each other out in a deafening cacophony. But as the universe expanded and cooled, it crossed a critical threshold, a phase transition where chaos didn't just fade but transformed. Like a magnet aligning its domains when cooled, the universe's quantum noise could have spontaneously locked into coherence, not despite the chaos but because of it. This idea isn't just theoretical. Lab experiments with ultra-cold atoms reveal how chaotic systems can abruptly synchronize under the right conditions. When researchers trap millions of atoms in a laser lattice and tune their interactions, something remarkable happens. The atoms, initially jittering in disorder, suddenly snap into a shared rhythm, as if an invisible conductor stepped in. Now scale that up to the universe's first microseconds. The same principles might have applied, with quantum fields acting like those atoms, their chaotic fluctuations, finding coherence through a universal phase transition. The cosmic microwave background's eerie uniformity could be the fossilized imprint of that moment, not a smooth starting point, but the aftermath of chaos tamed. But how? The answer lies in attractors, mathematical shapes that chaotic systems inevitably gravitate toward over time. In the early universe, the attractor might have been coherence itself, a state so stable that once the system neared it, there was no turning back. Picture a marble rolling through a labyrinth of hills and valleys. No matter where it starts, it eventually settles in the lowest valley. For the cosmos, that valley wasn't a place, but a state, a configuration where quantum fluctuations reinforced rather than undermined one another, creating a domino effect of synchronization. Critics argue that this pushes the limits of nonlinear dynamics, applying small-scale physics to the entire universe. Yet the math holds surprising promise. Recent simulations of quantum fields in expanding spacetimes show how chaotic initial conditions can indeed evolve into ordered structures, with coherence emerging naturally from the system's own feedback loops. It's as if the universe had a built-in recipe for turning noise into music, one that didn't require fine-tuning, just time and the right ingredients. The implications are profound. If coherence arose from chaos, then the universe's order wasn't preordained, it was learned, a hard-won achievement etched into the fabric of reality. And that changes how we see everything from black holes to dark energy. Perhaps they're not flaws in the cosmic design, but echoes of that primordial turbulence, reminders of the chaos that once birthed the harmony we call home. What if the very act of looking at the universe didn't just reveal its secrets but created them? This is the startling premise of observer-induced coherence, a radical twist on Eugene Wigner's famous thought experiment where consciousness doesn't merely perceive quantum reality but shapes it. Take this idea to cosmic scales and suddenly, the universe's pristine coherence isn't just a product of the Big Bang. It's a retroactive masterpiece stitched together across time by the collective gaze of every observer that ever existed, from the first hydrogen atoms forming stars to the human eyes peering through telescopes today. Wigner's original hypothesis emerged from the quantum measurement problem, the unsettling fact that particles exist in superpositions until observed, when they seemingly choose a definite state. But if a lone physicist in a lab can collapse a wave function by looking, what happens when you scale that up to the entire cosmos? Imagine the early universe as a storm of quantum possibilities, each potential reality vying for existence. In this view, coherence didn't emerge from the top down like a cosmic conductor guiding an orchestra. It crystallized from the bottom up as countless observations, from the simplest interactions to conscious beings, gradually voted on which version of reality would solidify. It's as if the universe was a fog of maybes, and every glance, every quantum handshake cleared a little more of the mist. The implications ripple through time in ways that defy intuition. If observers indeed shape reality, then the universe's first moments might have been provisionally coherent, a fragile quantum draft waiting for future confirmation. The cosmic microwave background's uniformity, the precise balance of physical constants, even the arrow of time itself could be the result of a vast, temporally tangled feedback loop where later observations reach back to reinforce earlier coherence. Think of it like a painter adding strokes to a canvas, except the painting also influences where the brush lands, an artistic paradox where cause and effect dance in circles. Critics dismiss this as solipsism dressed in quantum formalism, but modern experiments are testing boundaries between observation and reality. Delayed choice quantum eraser experiments show that measurements made now can seemingly alter events that already happened, as if the universe is retconning its own history. In one stunning variation, physicists observed quantum behavior in photons that had already been detected, suggesting that later choices can rewrite earlier decisions. If this retroactivity holds at cosmic scales, then the universe's coherence might not be a starting condition, but a consensus achieved across billions of years, with observers at every epoch acting as collaborators in a grand existential editing process. Here's where it gets even wilder. If observers are cosmic editors, then life isn't an accident, it's a necessity. The anthropic principle meets quantum mechanics in a feedback spiral where the universe's coherence allows for observers, and observers in turn sustain that coherence. Some theories even suggest that prebiotic processes, chemical reactions, stellar nucleosynthesis could have served as rudimentary observers, their interactions collapsing quantum states into the stable building blocks needed for complexity. It's a vision of reality where the line between observer and observed blurs, and the universe becomes less a machine and more a conversation, one that's been quietly unfolding since the very first quantum whisper. So the next time you look up at the stars, consider this: you might not just be witnessing the universe's history, you could be finishing its sentence. Quantum Darwinism isn't just about survival, it's about persistence. The idea that our universe's coherence wasn't handed down by cosmic decree, but earned through a ruthless quantum selection process, gains even more weight with cutting-edge research into environmental decoherence. Picture a cosmic battlefield where trillions of potential quantum states flickered into existence in the early universe, but only a handful, those resilient enough to withstand the relentless noise of their surroundings, survived long enough to shape reality. These weren't the most elegant states or the most exotic. They were simply the ones that could be seen, the quantum configurations stable enough to imprint themselves on their environment over and over until they became the universe's default settings. Recent experiments with quantum dots and superconducting qubits reveal just how ruthless this process can be. When a quantum system interacts with its surroundings, whether stray photons, vibrations, or even other particles, its delicate superpositions collapse into definite states. But here's the twist: not all collapses are equal. Some states leave far more footprints in the environment, like a hiker trampling the same path through a forest until it's etched into the landscape. These redundantly imprinted states are the ones we perceive as classical reality, while their fragile counterparts vanish into obscurity. Scale this up to the cosmic level, and the universe's coherence starts to look less like luck and more like inevitability. A quantum version of fake it till you make it, where stability emerges from sheer repetition. What's groundbreaking is how this reshapes our view of cosmic fine-tuning. The precise values of physical constants, the strength of gravity, the mass of electrons might not be arbitrary. They could be the only configurations that could survive environmental decoherence, the sole survivors of a billion-year quantum pruning. Simulations of early universe conditions show how certain quantum field arrangements, when bombarded by the chaos of inflationary energy, didn't just collapse randomly, they converged toward stable attractors like marbles rolling into the same groove. This isn't just theory. Lab observations of quantum Darwinism in action, like photon states imprinting their information on multiple environmental degrees of freedom, mirror the proposed cosmic selection on a tabletop scale. But the most profound implication lies in the cosmic microwave background. Those faint temperature variations aren't just snapshots of density fluctuations. They could be the fossilized remnants of the universe's first quantum votes, the states that won the decoherence lottery. Some models even suggest that dark matter's elusive nature fits this framework. It might consist of quantum states that almost made the cut, stable enough to persist, but not to imprint redundantly, leaving them hovering at the edge of perception. Critics argue this verges on tautology. Of course, we observe the states that survived, the others are gone. Yet quantum Darwinism offers something deeper, a mechanism for how coherence emerged from chaos, not by design, but by the universe's own relentless editing. Every atom, every force might be less like a law of nature and more like a meme, an idea so contagious it outlasted all competitors. So when we measure the spin of an electron or map the curvature of spacetime, we're not just uncovering reality. We're reading the universe's oldest, most enduring graffiti. The universe might be whispering its secrets in a language we're only just learning to hear, a faint, holographic static humming beneath the fabric of reality itself. This isn't science fiction. It's the frontier of experimental physics, where projects like the Fermilab holometer are hunting for holographic noise, the telltale jitter that could prove spacetime isn't smooth and continuous but pixelated, like a cosmic image projected from a two-dimensional boundary. If this noise exists, it wouldn't just revolutionize our understanding of reality. It could be the smoking gun for quantum coherence in the universe's first moments, a frozen echo of the instant when the cosmos locked into perfect synchronization. The holometer, a deceptively simple device buried beneath the Illinois prairie, is essentially a pair of giant, ultra-precise laser rulers. By splitting laser beams down 40-meter arms and measuring how their light interferes when reflected back, scientists are listening for vibrations in spacetime itself, not gravitational waves from distant collisions, but something far subtler, a fundamental fuzziness, as if reality is built on a grid too fine for us to see. Imagine trying to watch a movie projected on a screen made of sand. No matter how sharp the image up close, you'd spot the grains. The holometer is our magnifying glass, searching for the grains of spacetime. And if they're there, it means the universe's coherence isn't just a happy accident, it's baked into the geometry of existence. Why would holographic noise point to early coherence? Think of it like a vinyl record. The music sounds smooth, but under a microscope, you'd see the groove's physical imprints of the sound waves. In the holographic universe, those grooves are quantum entanglement relationships etched on a distant boundary, and the noise is the residue of their pixelation. If the early universe was a coherent system, its quantum links would have been exquisitely synchronized, leaving behind a space-time structure so orderly that even as the cosmos expanded, its underlying grid would vibrate in detectable ways. The holometer isn't just measuring noise, it's eavesdropping on the universe's first conversation with itself, but the hunt isn't without controversy. Some theorists argue holographic noise should be drowned out by other quantum effects, while others predict it's too faint for any instrument to catch. Yet the holometer's initial results, though inconclusive, have tantalized researchers with anomalies that don't fit conventional models. It's like hearing a faint, unfamiliar rhythm in the static of a radio, maybe interference, maybe something profound. Future upgrades and next-gen detectors, like the proposed Cosmic Action Spin Precession Experiment CASPER, aim to listen deeper, tuning into frequencies where holographic whispers might ring clear. What's at stake isn't just a technicality, it's a paradigm shift. If space-time is pixelated, then the universe's coherence isn't emergent, it's fundamental, written into the pixels themselves. Every galaxy, every atom would be a holographic projection of quantum data, with the Big Bang as the moment the system booted up. And just as a glitch in a computer's memory can ripple through its programs, holographic noise might reveal where the universe's code is still running in the background, quietly sustaining the coherence we call reality. So while we wait for the next round of experiments, one thing's certain: the cosmos isn't just stranger than we imagined, it might be stranger than we can imagine, its deepest truths hiding in plain sight, waiting for us to decode the noise. What if the universe isn't just governed by quantum laws, but actively protects them? Imagine reality as a vast, self-repairing algorithm, where every particle, every force is part of an intricate cosmic code designed to correct its own mistakes. This is the quantum error correction model, a theory that recasts the universe's coherence not as luck or brute force stability, but as an elegant fault-tolerant system, a kind of cosmic antivirus software running silently in the background since the first moments of time. At its core, this idea borrows from cutting-edge quantum computing, where fragile qubits are shielded from decoherence by embedding them in error-correcting codes. These codes don't just detect flaws, they actively repair them, spreading quantum information across multiple qubits so that even if one fails, the data survives. Now zoom out to the scale of the cosmos. In the early universe's seething quantum foam, fluctuations should have ripped coherence apart, yet somehow it held. The error correction model suggests why. Space-time itself might be woven from a similar redundancy, with every particle state mirrored and distributed across hidden dimensions or entangled networks, creating a buffer against chaos. Think of it like a symphony where every musician knows not just their own part, but everyone else's, so even if one misses a note, the music plays on uninterrupted. The math behind this is as breathtaking as it is precise. Certain error-correcting codes, like the holographic code derived from string theory, naturally embed geometric relationships between quantum bits that mirror the structure of spacetime. In simulations, these codes generate emergent properties like locality and causality that look eerily similar to the universe's fundamental rules. It's as if the cosmos booted up with its own operating system, one where coherence wasn't a feature but a requirement hardwired into the code. Even black holes, those infamous data destroyers, might fit this framework. According to some theorists, the information swallowed by a black hole isn't lost, it's scrambled and stored holographically on the event horizon, a cosmic fail-safe ensuring nothing ever truly vanishes. But here's where it gets even more profound. If the universe is error-correcting, then the constants of nature, the finely tuned numbers that make life possible, might not be accidents. They could be the only stable configurations in a vast landscape of possible codes, the ones resilient enough to withstand quantum noise across billions of years. Dark energy, that mysterious force accelerating cosmic expansion, might even be a relic of this correction process, a kind of cosmic update smoothing out glitches in spacetime's fabric. Experiments are already hunting for evidence. Researchers analyzing quantum gravity simulations have spotted error-correcting behaviors in the way spacetime stitches together at microscopic scales. Others probe the cosmic microwave background for anomalies, subtle deviations that could hint at a universe rewriting its own initial conditions to preserve coherence. Even lab-based quantum networks, where entangled particles resist environmental noise, offer glimpses of how cosmic-scale error correction might work. This isn't just theory, it's a paradigm shift. If reality is a self-healing code, then the universe isn't just ordered, it's resilient, engineered to endure. Every star, every atom could be a testament to an ancient, unbroken protocol, whispering across time that coherence isn't the exception but the rule. What if the universe's perfect coherence isn't a natural phenomenon at all, but the telltale signature of a simulation? This isn't just sci-fi speculation. It's the simulated coherence hypothesis, a radical twist on philosopher Nick Bostrom's famous argument that our reality might be an advanced civilization's digital creation. Think of it like this: when programmers build virtual worlds, they don't simulate every atom individually. That would demand infinite computing power. Instead, they use optimization tricks, rendering only what's observed and filling the gaps with mathematically elegant shortcuts. Could the universe's eerie coherence, the way quantum laws hold firm across billions of light years, be the glint of those shortcuts, the cosmic equivalent of a video game's procedural generation? Bostrom's original simulation argument rests on probability. If civilizations inevitably create ancestor simulations with consciousnesses indistinguishable from real beings, and if those simulations outnumber base reality, the odds we're in the original universe shrink to near zero. But the simulated coherence hypothesis goes deeper, suggesting that the very structure of our physics, the way particles entangle, the reliability of constants like the speed of light, are artifacts of efficient coding. A truly chaotic universe would be computationally expensive. A coherent one is elegant, compressible, and easier to sustain. It's the difference between streaming a perfectly rendered movie and trying to broadcast static. One follows rules, the other drowns in noise. Look around, and the evidence, or at least the hints, might be everywhere. Quantum mechanics, with its observer-dependent reality, mirrors how video games render graphics only when a player looks. The universe's mathematical beauty, from the golden ratio in galaxies to the precise values of fundamental constants, could reflect a programmer's preference for clean, efficient equations. Even the infamous Planck length, the smallest possible unit of space, might not be a physical limit but a pixel size in the simulation's code. The holographic principle we explored earlier fits snugly here. If our 3D reality is projected from a 2D boundary, it's exactly the kind of data compression a simulation would use to save memory. But here's the twist that separates this from mere techno-mysticism. If we're in a simulation, its creators wouldn't want it to crash. Coherence, in this view, isn't just aesthetic, it's functional. Glitches in the matrix, like particles teleporting or constants drifting, would risk fatal errors, so the system enforces ironclad rules, error correcting in real time to maintain stability. This might explain why quantum decoherence, the collapse of superposition, happens so reliably. It's not a law of nature, but a firewall preventing computational overload. Even the arrow of time could be a feature, ensuring events process in orderly sequence rather than chaotically backtracking. Skeptics counter that, positing a simulator just kicks the can down the road. Who created their universe? Yet the hypothesis thrives precisely because it's hard to falsify. How do you prove you're not in a simulation when all your tools are part of it? Some, like Elon Musk, argue that rapid advances in VR make the idea plausible. If we're nearing photorealistic simulations with conscious NPCs, why wouldn't others have gotten there first? Others, like physicist Seeler's Bean, suggest hunting for jaggies, anomalies in high-energy particle behavior that might betray the simulation's resolution limit, like seeing pixels if you squint at a screen. Whether you buy the argument or not, its power lies in reframing the cosmic question. If coherence is programmed, then the universe isn't discovering its laws, it's executing them. The symmetries we marvel at, from the spiral of galaxies to the bonds between atoms, might not be fundamental truths but design choices. And that leaves us with a chilling, thrilling possibility. The greatest scientific quest to uncover the universe's deepest rules could actually be a process of reverse engineering someone else's code. So the next time you gaze at the stars, ask yourself, are you seeing nature's masterpiece or the glow of a celestial server humming softly in the dark? From the cosmic symphony of a Bose-Einstein condensate stretching across the infant universe to the holographic whispers of a two-dimensional boundary encoding our 3D reality, these 30 theories reveal something extraordinary. Quantum coherence isn't just a footnote in physics. It's the hidden architect of existence itself. Whether through the delicate braiding of onions weaving space-time into existence, the self-repairing code of quantum error correction silently maintaining cosmic order, or even the spine-tingling possibility that our universe's perfect synchronization points to a simulated reality, one thread ties them all together. Coherence bridges the unlikeliest gaps in our understanding. It's the Rosetta Stone translating between quantum strangeness and cosmic structure, between the chaos of the Big Bang and the delicate fine-tuning that allowed galaxies and life to emerge. What's breathtaking is how these ideas transform the universe from a static stage into a dynamic, almost living system. The holographic principle suggests reality is a projection. Loop quantum gravity paints it as a spinning tapestry of threads, and the transactional interpretation frames it as a conversation across time. Yet each theory, no matter how wild, shares a moment of reckoning, a pivotal instant when coherence took hold and turned potential into reality. Even the most radical ideas, like the simulated universe hypothesis or Boltzmann brains, ultimately hinge on whether quantum synchronization is a fluke or a fundamental feature of existence. And that's the real magic. Coherence isn't just a tool for physicists. It's an invitation to marvel at how fragile and resilient our universe truly is. So here's the challenge for you. Which of these theories sparks that electric sense of wonder? Is it the poetic elegance of Penrose's cyclic cosmology, where universes rebirth themselves through quantum echoes, or the visceral punch of the black hole genesis theory, where our cosmos blooms from the wreckage of another? Maybe the sobering beauty of quantum Darwinism, where reality is the last survivor of an ancient selection process, speaks to you. Whatever it is, let's keep the conversation rippling across the cosmos. Drop your thoughts below, hit subscribe, and join us for the next journey into the unknown. After all, the universe's greatest mysteries aren't locked away in some distant galaxy. They're hiding in plain sight, waiting for us to piece them together, one coherent whisper at a